Section 29.7, Excited States and Spectra. So we've learned about the nature of the atomic levels for multi-electron atoms and how the restrictions that are placed on the quantum numbers and on the ability of no two electrons to fill exactly the same state, we've seen how that gives rise to an understanding of the structure of the periodic table. So let's now look at some of the excited state characteristics of these atoms and their atomic spectra. First of all, it's important to note that the ground states of electrons are important because the ground state of an element corresponds to the state in which it spends most of its time. Any atom, for the most part, is in its ground state and can be excited to one of the excited states, but it quickly makes a transition back to the ground state. So it spends the majority of its time in the ground state. On the other hand, the excited states hold the key to understanding the light patterns that are given off by atoms, i.e. the atomic spectra. So let's consider sodium for a moment. Its ground state configuration, because it's Z equals 11, it has 11 electrons. The first two go in the 1s state. The second two go into the 2s state, the next 6 go into the 2p state, and then finally the 11th electron goes into the 3s state. And what I want you to notice is that the first 10 electrons are, they fill a complete shell, and so they form a closed shell. And that closed shell actually corresponds to neon. 10 electrons is what neon has, and since neon is a noble gas and therefore is chemically rather inert, it is that way because of the fact that its electrons form a closed shell. The 2p6 shell is now closed, and the overall configuration of those electrons is not chemically reactive. On the other hand, when we add one more proton to make sodium and one more electron to make it neutral, the next spot for that electron is in the 3s state, which is chemically a very active state because it's the only electron in that state and is not paired up with any other electrons and is certainly not part of a closed shell. So the 3s electron is called the valence electron, and it can be excited to higher levels. For example, it can be excited from the 3s to the 3p state. We can make an excitation to the 3p state, and so this would be the configuration then for the first excited state in sodium, as opposed to the ground state, which is the one that ends up in the 3s shell. So this figure then shows what goes on with sodium as far as the levels go. Here's the ground state, the 3s level, and we define that as 0 because it's the ground state energy. It has energy equals 0 relative to the levels above it. Notice its actual energy is negative because it's a bound atom, but for our purposes we always establish the ground state as having 0 energy and all of the states above that as having positive energy, which then allows us to understand both the excitation and de-excitation of atoms by the absorption or emission of a photon, and the energy of that photon has the same energy as the difference between the two states involved in the transition. So here's some of the states and the energies of those states for sodium. We have the 3s ground state, the next excited state is the 3p, the next higher state is the 4s, and then we have the 4p and the 3d states. Now there are rules that govern the transitions in atoms. We'll get to those in a moment. Not all transitions are possible. They are bound by certain restrictions on the quantum number little l. So just to reestablish the fact that excitation is the process of getting an atom into its excited state. So if a photon comes in to a state in its ground configuration, E1, that photon can be absorbed and the energy of the electron can be promoted to the E2 state, provided that the photon has the appropriate energy that corresponds to the difference in those energy levels. Other photons will not excite the atom, but those that have the energy difference between the states, or the energy of the photon corresponding to that difference, constitute photons that can excite the atom to its excited state. The Bohr model says that the atom can jump into a higher state by absorbing the photon, and the photon frequency is equal to the delta E, separation in energy of the two states, times Planck's constant h. And in terms of wavelength, then, we can calculate lambda from that delta E, the energy difference between those two states, which is hc over delta E, which we can call 1240 eV nanometers because h times c is equal to 1240. The units are eV nanometers. So this makes it a simple way to characterize the wavelength of the emission going from state E2 to E1, where the difference between the states is delta E, and all we need to do is divide that delta E into 1240 eV nanometers to come up with the wavelength for that particular transition. Now, there is something called a selection rule, which governs the ability of an atom to negotiate changes between states. Not all quantum jumps are allowed. The selection rule says the following: transitions, either absorption or emission, from a state with orbital quantum number l can occur to only another state whose orbit quantum number differs by plus or minus 1. Delta L, the change in L in going from one state to another, has to be plus or minus 1, meaning that we can only go from, for example, an S state to a P state, or a P state to a D state, but not an S state to a D state, nor can we go from an S state to another S state, because in those two cases, delta L is equal 2 for the S to D state transition, and delta L equals 0 for the S to S transition. So we find that in nature, the most common transitions are ones that abide by this selection rule, which says that in negotiating either an absorption or an emission of a photon, we have to do it in such a way as to go from one state to another that differ in their orbital angular momentum L by 1 unit. I also want to remind us that we can excite atoms by collisions, and the collision process is one by which the energy of that impact between atoms can cause the atom that was hit to be excited to a higher state. And so the collision knocks the electron to a higher state. Collisional excitation differs from excitation by absorption, on the other hand, because in a collision, the particle is still present after the collision, and it does not have to transfer its entire energy. And so you can collide with an atom, knock it into an excited state, and it will have extra energy that corresponds to whatever leftover there is in terms of kinetic energy. So the two particles can collide, and in doing so, one can excite to a level, but it doesn't have to have exactly the same collisional energy as that required to promote it to that next state. And so collisional excitation is allowed. It can excite atoms much more easily as long as they have at least enough energy to promote that atom to an excited state. Collisional excitation is denoted by this schematic right here. There's a particle or an atom in state E1, and the collision happens. Something collides with that atom, and it transfers from the state E1 to E2, and the leftover energy of the particle that hits that atom will go off with whatever is left over. So the energy of the particle will have greater than or equal to the energy difference, and it will go off with kinetic energy representing the balance of energy that it had, part of which was used to promote the atom to an excited higher state, and part of it which is in terms of kinetic energy, both of that particle and, it turns out, of the atom that it hits, because momentum and energy are also conserved in that collision. So it can also impart some kinetic energy to the atom that was hit as well. Okay, so the emission spectrum then of an atom corresponds to the emission is for the emission of a photon, and the promotion from a lower state to a higher state is by the absorption of a photon. So we see that in this particular case, if we excite the state from the ground state to this particular excited state, it can get back to the ground state either by decaying right back down to the ground state, or it may have alternative paths based on levels that might be intermediate between that state and the ground state. As long as they abide by the delta L equals plus or minus 1 rule, they can occur in the atom. Also, atoms have a typical lifetime, which is on the order of about 10 to the minus 8 seconds, a few nanoseconds. And we don't actually have the ability to calculate the exact time that a particular atom is going to exist before it makes that transition to the ground state, but we can calculate the average time. The uncertainty principle does not allow us to know how a particular atom will be in an excited state. But the average of atoms, a big collection of atoms all in that excited state, can be measured, and that average value is called the lifetime of the state. And as I said, it's typically only a few nanoseconds. The lifetime of the state is variable from atom to atom, but on average, if you have a large ensemble of those atoms, say 1,000 of them, then the average of the time that those 1,000 atoms are going to exist in their excited state before decaying to the ground state is what we call the lifetime of the system, even though any one individual atom can't be known for the exact time that it's going to exist. All we know is the statistical nature of that transition based on a number of transitions that have an average value. So in sodium, element number 11, here's what the excited state structure looks like and the ability for this state to be excited and to de-excite back to the ground state. These are some of the possible transitions. Notice the ground state of sodium has its valence electron in the 3s shell, and so if we put it into any excited state, it can make its way back down to the ground state by negotiating whatever transitions and levels are available that abide by this angular momentum rule. So let's just say, for example, we put the sodium in the 5s state. It cannot make a transition to the ground state. That's not allowed, because that would be an S to S state, and according to the delta L equals plus or minus 1 rule, that's not allowed. On the other hand, the 5s state is perfectly free to make a transition to the 3p state, because that goes from an S to a p state, and that represents an angular momentum change of 1, and therefore is allowed. And then the 3p state can make a transition to the ground state via another transition that involves delta L equals 1. So these are allowed transitions. Basically, the rule says that if I'm in this column, I can transition to this column, and if I'm in the second column, I can either transition to the one to the right or to the one to the left, because both of those, the first one represents a P to a D transition, and the second represents a P to an S transition. So as a result, notice that the 5p state has a couple of options. It can go straight to the ground state because that's a P to S state, and that's allowed. It can go to the 4s state, which is also P to S, which is allowed, after which that 4s state has no choice but to go to the 3p state, and that 3p state then goes to the ground state. And then finally, this 5p state can execute a transition which involves first the 5p to 3d state, which is allowed because delta L equals 1. The 3d state can then transition to the 3p, which then transitions to the ground state. So this 5p state, if populated by the absorption of a photon, has a number of ways to get back down to the ground state, each of which involves transitions that have different energies, and therefore the spectrum for the de-excitation of 5p is going to involve several different lines with different colors based on the energies of those transitions that are involved. And as we can see in this particular diagram, there are 3 paths to do that. The 5p to the 4s transition, which involves 3 photons to get to the ground state, the 5p to the 3d state, which also involves 3 photons to get to the ground state, and then the 5p to the 3s state, which has 1 photon, and it's the largest of all the photons. So this particular transition, this one straight to the ground state, is going to have the highest energy and therefore the highest frequency in this particular collection of transitions from the 5p state on down. So here's what the transitions for sodium look like. This figure is for sodium that would be recorded by a spectrometer. The series of emission lines near 300 nanometers down here are due to all possible transitions to the 3s state, all possible NP transitions to the 3s state. So N would represent the principal quantum number, and P represents the L equals 1 orbital, the P states. So these are all the P state transitions to the ground state of sodium, the ones around 300 nanometers. It's also possible for an atom like sodium, for example, to be hit by an X-ray. And X-rays have very, very small wavelengths, smaller than the size of the atom, and a very high-speed particle is capable of knocking inner shell electrons out of the target atoms, producing shell vacancy. It can also be vacated or knocked out by, basically the idea is that the atom can be ionized by either removing the valence electron, which is a very low energy process, and typically our energies near the visible spectrum, but it can also be knocked out by a very high-speed particle capable of knocking out one of its inner shell electrons. And those X-rays then result because when we knock an inner shell electron out, those electron orbitals are so tightly bound to the nucleus that they have very, very high energy, and the difference between neighboring levels is also very high. The heavier the atom, the more tightly bound the inner shell electrons are. So if I can knock one of those inner shell electrons out and leave it vacant, the states above that, which are going to fill that ground state or that vacancy, have very high energies because of the fact that those inner shell electrons are so tightly bound. So the photon that's given off ends up being in the X-ray region. And so we can see X-rays coming off a sample that's being bombarded by very high energy electrons, which is evidence of the fact that the high-energy electrons are knocking out inner shell electrons and creating a vacancy in that atom, which is very tightly bound, and therefore the transitions of neighboring electrons to it also involve very large energy differences, creating these X-ray photons. In heavy elements like copper or iron, the energy difference is quite large, and because they're getting to be quite heavy atoms, and the transition from, for example, the 2p to the 1s state, if it's the 1s electron that's vacated, have very small wavelengths indeed. 0.1 nanometers is about the size of a hydrogen atom, and the higher the element, the higher those transition energies, and therefore the smaller the wavelength of the X-ray. So for example, in uranium, if I bombard uranium with a stream of very high-speed electrons, and I can knock out some 1s electrons, those uranium transitions are going to be very high indeed in energy, because the 1s and the 2p level in uranium are separated by a large difference, because those 1s electrons are so tightly bound, sitting so near a nucleus that has such a high charge as uranium does. So the X-rays that come then from transitions in heavy elements who have had their 1s electron knocked out are primarily from the 3p and the 2p levels. In this particular state, you see that the energy of those states is quite high indeed. The energy is listed along the y-axis here. The 2s state and the 2p state are around 8,000 electron volts, which is 8 kiloelectron volts, or 8,000 electron volts, which is in the X-ray range. And so if I excite an atom, if I vacate a 1s electron in a fairly heavy atom, this represents the possibility of transitions from the 3p and the 2p state, both of which are allowed to make transitions to the ground state by the L transition rule, and so either can do so. And so we would typically expect to see two different energies of X-rays coming off of this particular sample when bombarded by high-energy electrons.